Hi, my name is Nicholas Espinal. This is the third question for my Chapter 27 quiz, and this is what it asks. As shown in the figure, a small particle of charge q, which is -7 times 10 to the -6 coulombs, and mass m, which is 3.1 times 10 to the -12 kilograms, has velocity 9.4 times 10 to the 3 meters per second as it enters a region of uniform magnetic field. The particle is observed to travel in a semicircular path shown, with radius equal to 5 centimeters. Calculate the magnitude and direction of the magnetic field in the region. So first we have to ask ourselves, how can we relate the path of a charged particle to a magnetic field's magnitude and direction? From our notes, we know that the radius of a particle's circular path is given by m times v all over q times b, where m is the particle's mass, v is its velocity, q is the charge, and b is the magnetic field. And when we assume that the path is clockwise, the sign of the magnetic field will actually determine whether it's pointing inward or outward. So we have this equation, and we have 4 givens and only one unknown, the magnetic field. The radius was given as 5.5 centimeters, so we can convert it to 0.005 meters, and we can solve for b. So when we solve for b, we're going to have b is equal to m times v all over q times r. So we have this equation. We have all of our givens, so we're just going to input the values. And when we input the values, we're going to get negative 0.805 Teslas. And the negatives is telling us that it's actually pointing into the page. But how can we actually visualize this and prove this? So we know that this is the path of the particle. This is the tangential velocity of that particle. And in order for it to curve in this direction, there needs to be a force. And this is the force on the negative charge when it's in the region of the magnetic field. And we know from our notes that the force on a negative charge is in the opposite direction of the force on a positive charge. So we can use this information to determine which direction the magnetic field is pointing. So we know that the force on a positive charge, if the charge we were given was positive, will be pointing in the opposite direction, and we still have the direction of the velocity. So on using a three-dimensional coordinate system, and we plot these, this is the velocity and this is the force on a positive charge. The force is supposed to be equal to the cross product of the velocity and the magnetic field. So in order to have our answer, our cross product, to be in the negative j direction, and with our velocity pointing in the negative I direction, the only possible way for this magnetic field to produce this would be that it has to point in the negative k direction. If we use our right-hand rule and we point our hand in the direction of the velocity and then curve it down to the direction of this magnetic field, then the force will be pointing in that direction for a positive charge. So meaning that the force on a negative charge would be in the opposite direction, and it would give that force that we would need for this charge to go in that path. So if the IJ plane is the page, then B is the magnetic field is going to be pointing into the page. So we have this velocity and we have this force on the negative charge. Thus, the magnetic field is actually going to have to be pointing into the page, as we see here, to create that cross product, which is a negative cross product, to create that force that is needed to create this path for the particle. So to answer this question, we found the magnitude to be 0.81 Teslas, and it is pointing into the page. Thank you.